welcome. This will be my video on going over the first midterm, term test one, midterm, same thing, for MAT235 multivariable calculus. And yeah, the coverage is right over here. So, yeah, so the coverage right over here. So term test one covers these sections over here from the textbook, and I will link a Google Drive link as well as some other relevant links for many different resources for MAT235 that I've used myself and personally have found useful throughout the course. But yeah, let's get into it. So this first part over here, this part is the short answer part, which again, you're only graded on your final answer. So you don't need to show your work, but it's always fun to show it like on the side. So let's get into it. So in this case, we have r squared is equal to sine theta. It's a polar equation. We want to find a point r comma theta other than 0, 0 that lies on this curve. And again, we can remind ourselves what that means. Again, a point lies on the curve simply if the point satisfies the equation, meaning if you plug in the corresponding r and theta values, you will get an equality. So the way we can approach this, usually it's easiest if we just pick r to be something reasonable and plausible, obviously. So you can either pick r to be 0 or 1. Negative 1 obviously works, or not, sorry, negative 1 wouldn't work. Obviously, r has to be greater than 0 because it's r squared. But in this case, does r have to be? Anyways, regardless, 0 and 1 are your easiest options to go with. I'll just go over both cases. So in this case, if you pick r is equal to 1, so let's say if you pick r is equal to 1, what you then get is, again, 1 squared is obviously just 1. So you get 1 is equal to sine theta, or sine theta is equal to 1, same thing. So now you're just looking for, again, values of theta, where sine of theta is equal to 1. So obviously you have pi over 2, and any 2 pi addition of that. So in this case, you then have your r theta. Again, r you fix to be 1. So you have 1, then pi over 2. Add 2 pi to pi over 2. You get 5 pi over 2. And then you can keep going on like this. Again, all of the answers are valid. You're just looking for one other point that, again, lies on the curve. The other case is when r is equal to 0, which, again, follows a pretty similar process. You just get 0 is equal to sine theta, which then tells you that your points r comma theta will be of the form, again, r is fixed to be 0. Now you're just looking for points where sine of theta is equal to 0. So obviously 0, 0 is a point, but as per the question, other than 0, 0 is the point we're looking for. So again, obviously, sine of an angle is equal to 0 for 0, pi, 2 pi, etc. So you have, let me change my eraser. Again, so you have 0, then pi, 0, 2 pi, and so on and so forth. So this question, pretty straightforward. Again, just keeping in mind that polar coordinates have many representations pretty much. Okay, next we want to write the Cartesian coordinates -3, negative root 3 as polar coordinates. With this, you really need to keep in mind what quadrant you're dealing with. So in this case, both the x and y values are negative, meaning if you draw out your coordinate system, you're going to be in quadrant 3. Right, so again, if you draw out your coordinates, this is quadrant 1, 2, 3, and then 4. Right, and again, here, quadrant 3 is where both x and y are negative. And again, this is important because polar coordinates have multiple representations, again, as I mentioned in the previous question. So it's really important to keep that in mind. Okay, so for this, you can do it a few different ways. I'll try to go over the simplest way of going over it. So it's always good to always remind yourself, or at least write out the relevant equations. So you have x is equal to r cos theta, y is equal to r sine theta, and then x squared plus y squared obviously is equal to r squared. And then also, this one you don't have to make use of. I believe the solutions provided by the instructors do use this somehow, some way, but you have that tan theta is equal to y over x. And this you can easily derive simply using the fact that you know tan theta is equal to sine over cos. And obviously, if you divide these two, the r's will cancel out, and you're left with sine over cos, which is y over x. I personally like using the method where you just use one of these. I just went with x. You could definitely use y as well. But obviously for R, you're going to need to use this one first. So we'll do that first. So again, I'll rewrite it here. So you have x squared plus y squared is equal to r squared. Plugging in the values, you again know that x is -3, y is -√3. So you have -3 squared plus -√3 squared, which is equal to r squared. Again, if you simplify this, -3 times -3 is +9. -√3 times that -√3 is +3. So you have 9 plus 3, which is 12. Which then means that r is equal to √12, which you can also write as 2√3. Again, we get this by, if you imagine factoring out a 4. So you can write this 12 as root 4 times 3, which is √4 times √3. This is obviously 2, so you get 2√3. Okay, from there, we can again make use of either or. I simply just choose to go with x. So you know that x is equal to r cos theta. Again, if I didn't make it clear already, we're currently trying to solve for theta now. Because we have r, we're looking for theta. Again, we're looking for polar coordinates. So in this case, we can plug in all the values we know. We again know x is -3. So you have -3. And then r, we just solve for over here, is 2√3. So -3 is equal to 2√3 cos theta. Then dividing both sides by 2√3, we then get that as follows. So we get cos theta is equal to -3 over 2√3. Here, again, you can rationalize the denominator by multiplying the top and bottom by √3. You get -3√3 over 2 times 3. So again, we multiply the top and bottom by √3. √3 times √3 is just 3, and then 2 times 3 is 6. And then now you can divide 3 and 6 to get -√3 over 2. So if you follow the chain of equalities, we know we're looking for cos theta is equal to -√3, meaning again, we're looking for a value of theta in in quadrants 2 and 3. So in this case, just check to make sure. Yeah. So in this case, you know that theta. So you can think about it this way. We know that if we just ignore the negative, we know that cosine of some angle is equal to √3 over 2. If we're just dealing with angles between 0 and 90. We know this happens for pi over 6, right? And again, you can always also picture the graph. You know that the higher point here happens earlier on, so pi over 6. What we're looking for where it's negative, and we know cosine again is negative in quadrants 2, quadrants 3. So in this case, you have 5 pi over 6. Or, of course, you also have the other option. So again, pi over 6 is kind of like the, I forget the terminology. I'm not sure if it's primary or it's some kind of terminology in terms of the arms. But you have pi over 6 in the first quadrant, and obviously to find the equivalence, but negative in the second and third quadrant, you can add and subtract pi over 6 from 180, or 180, sorry, or from pi. So in this case, pi minus pi over 6 would give you 5 pi over 6. Pi plus pi over 6 would give you 7 pi over 6. And this is now where we, again, have to remember what quadrant we're dealing with, right? Again, these are both negative, so we're somewhere in quadrant 3. And if we imagine our angles, we know that pi over 6 is over here, 5 pi over 6 is here, and 7 pi over 6 is somewhere over here. So obviously, in this case, we must use 7 pi over 6. Here, I should also write the answer here. For the first part, we'll just go with 1 comma pi over 2. In the back here for number 2, again, we only have one answer here because for Cartesian coordinates, there's only really, or there isn't only one representation, sorry. In this case, because we're using polar coordinates, obviously this can be any, this plus 2 pi times like some integer n. But in this case, obviously we don't need to do that. So it's just extra. So in this case, we know that again, r is equal to √12 or 2√3. And we know our angle theta, so r comma theta, so 7 pi over 6. What you'll notice is, and again, for the next question or for some following question, you'll see the same idea. The way you leave your answer isn't too important, as in like if you simplify your root fully or if you don't. As long as you have the right numbers, for the most parts, you'll get the answer correct. There are some specific cases where obviously you will need to simplify in order to get a different final answer. Yeah. Okay. Number three, this is again just a simple cross product question. So we're going to use again that Mr. Farad strategy for finding the cross product. In this case, one big thing you have to keep in mind is that the cross product only really makes sense in R3, meaning in 3 space. In this case, we only have I and j, meaning we can just assume that the z component or z component is equal to 0. And again, this is in a slightly different notation than just our typical like square bracket notation. Here we have the unit vectors I, j, and k. K would be 0 in this case. So in this case, we just have to read off the coefficients basically. So we're going to first rewrite u as we'll write it in the bracket vector notation. So again, I hat is kind of like the first component. The coefficient is just 1. J is the second one, so it's positive, and then Z obviously is 0. V, on the other hand, slightly different. They try to trick you up a bit by switching the order. Again, the order doesn't matter. The letter itself matters more. So in this case, the coefficient in front of I hat or of I hat is -1. J hat is 1, and then again, Z, or sorry, Z, but that K hat is equal to 0. So once you have these, you can now compute the cross product. Again, I do have a video on that. Remember, you can either use this kind of crisscrossing method, or you can use the determinant method. Completely up to you, up to preference. In this case, I again personally enjoy just the crisscross method. So we'll do that. We have 1, 1, 0. So 1, 1, 0, 1, 1, 0. Then -1, 1, 0, -1, 1, 0. Cross out the farthest left and right, and then now you can do the crisscross or whatever you want to call it. So in this case, I'll show you here. So U cross V. So we have 1. Here we have 1 times 0, which is 0. And then minus 1 times 0, which is 0. So you still have 0 here. In this case here, you have 0 times -1 minus 0 times 1. So still 0. And then finally, you have this right over here. So you have 1 times 1, which is 1. So I'll just write it here in using highlighter, but I won't actually write it out. So you have 1 times 1 minus -1 times 1. So 1 times 1 is 1. And then negative or minus -1 times 1 just becomes +1. So you get 2 in the k component. And this right here would be your cross product. So you can either express your answer in the bracket notation we're currently using, so 0, 0, 2. Another accepted answer is also just 2 times the k hat vector, just like that. Okay, and then number 4, this is where we have a vectored value function. In this case, I'm not sure if that's the right terminology, but the point is the components of our vector function are functions. In this case, we're computing the second derivative of r of t. So to do that, it's exactly like we do in just single variable calculus, where we're just taking the derivative twice to find the second derivative. So again, remember when we take the derivative of this, we're taking it by parts, or not by parts, but by like each component. So in this case, r prime of t. First component here, t squared, we just take the derivative of that. So just 2t. E to the -3t, again, is just e to the -3t times the derivative of that inside part, which is -3. You have -3 e to the -3t. And then cos squared of t, again, you can treat as cos of t squared, which again, you can just use combination of power rule and chain rule. So you have 2 times cos of t times the derivative of the inside, which is negative sine of t. Again, this I'm going to rewrite in one line as just -2 and then sine t cos t. So -2 and then sine t cos t. From there, we just need to take the derivative once again. So we have r double prime of t. In this case, 2t, obviously the derivative is just 2. Here, we just have -3 times the derivative of this, which is again just the same thing over here. So you have 9 e to the -3t. And finally, here you can apply a product rule. Here, I'll just write it on the side. So you have -2 times the product rule. So first, times the derivative of the second, which is negative sine t, plus second, times the derivative of the first, which is cos t. And in this case, you can then expand this, which would then give you, you have -2 times, you have this -2 times negative sine squared t. So you have 2 sine squared t. And then here you have negative 2 times cos squared t. So you have minus 2 cos squared t. And this would be your final answer right over here. Oops. Right over here. So I'll just copy it and put it up here. It is oddly formatted in the sense that it doesn't fit in one line, but it doesn't matter. Yeah. Okay, moving on. We're going to be matching equations with graphs. In this case, the best process usually, again, is process of elimination. And the way you would do that here is mostly just basing off of key points and the general shape. So there's a way to tell the general shape of any of these. You can try it in Desmos by simply just plugging in x or y is equal to 0 and seeing where the other points go. The other method, which I'll demonstrate here, is to simply factor this as much as possible and then finding the, again, I'm going to butcher the terminology, but like the center of the ellipses. In this case, we have ellipses here, not just circles. But yeah, so let's get into that. First case here, we can, we'll rearrange it first, just so it's super clear what we're doing. So we have x squared and then minus 6x. So I'm just going to collect the x's and the y's together. Plus 4y squared plus 8y is equal to 3. From here, we're going to complete the square twice. So this is again where grade 10, grade 11 math comes in handy. So we have x minus 3 squared minus 9 plus 4 times y plus 1 squared minus 4. This is equal to 3. I'm realizing I'm writing a little too big here. Let me move this over a bit. Okay, and then from here, we can just simply add 9 and 4 to both sides. What you're left with is x minus 3 squared plus 4 times y plus 1 squared. Then you add over the 9 and the 4, and you should get 16, right? 9 plus 3 is 12, plus 4 is 16. So in this case here, you're able to directly tell because obviously these two are not ellipses. So it's either between A and B. In this case, we know that our the center of our ellipse is at 3, comma, negative 1. Again, just finding the values of x and y that make the inner parts 0 correspondingly or respectively. So 3, negative 1. And if we look over here, so again, we count 1, 2, 3, and you go down by 1, you get this exact point over here, which again is 3, negative 1. And again, you can also verify that when the y part is scaled by 4 or has a 4 that's multiplying it, it kind of expands in that way. But yeah, so in this case, we have that this is A. This I can tell you is B already, just obviously by process of elimination, but this one I'll also show you why that's the case. So here, again, same exact idea. We're just completing the square. So you have 4 times x. So here the idea is you have 4 times x squared plus 2x when you factor out the 4, and then you can just complete the square as you normally do. So plus 1 squared minus 4 plus y minus 3 squared is equal to 12. And then, again, we just add over the 4 to both sides. So then on the left, you're left with x plus 1 squared plus y minus 3 squared is equal to 16 again. But in this case, notice it's slightly different. We have negative 1 comma 3. And right here, negative 1, 1, 2, 3. This is the center again, right over here. So negative 1 comma 3. So that's how you know it has to be B. For number 3, in this case, we notice that the x's have kind of multiple terms in terms of x and x squared, and the y, there's only just that flat linear y term. So if we rearrange this, we get 2y is equal to negative x squared plus 2x plus 5. And then from here, we just simply divide both sides by 2, just so it gets it into the y is equal to something form. So y is equal to negative 1/2 x squared plus x plus 5 over 2. And then I'll also just do the simplification for 4 before continuing. And in this case, we have things the other way around, where you have just one linear x term, whereas the y, you have linear and quadratic terms. So simplifying, you get 2x is equal to y squared plus 2y minus 7. And again, dividing by 2, you get that x is equal to, I don't like the way I drew that x. X is equal to 1/2 y squared plus y minus 7/2. From here, it's pretty clear that whenever you have something of the form y is equal to, again, just ax squared plus bx plus c, you have a typical parabola that opens up. So obviously, or up or down, sorry. But c in this case would be your answer here. And then obviously by process of elimination, d would be over here. But same ideas keep kind of hold true here. You're basically just reasoning with what typical graphs would look like. In this case, I want to say there's a printing error because if you do calculate the vertex or the y-intercept, they'll be off. But regardless, the general shape, that idea is what you're looking for. Okay, number 3, we're told that a curve is parametrized by x of t is equal to t squared minus 3, and y of t is equal to t cubed minus 4t, for t between -2 and 2 inclusive. So we're looking for an expression for dy dx in terms of t. And again, this really just involves parametric equations and parametric calculus, which is what you will start out with. So in this case, we generally just have dy dx is equal to dy dt over dx dt. And then from here, we can just individually calculate dx dt and dy dt. Let me just get that here. Yeah, very good. So we have dy dt. Also realizing I'm writing a bit small, but yeah, you can deal with that. So dy dt, we again know that y over here is t cubed minus 4t. Taking the derivative with respect to t gives you 3t squared minus 4. Then dx dt, same idea. You have t squared minus 3, except in this case, you just have 2t. Putting these two together, you just get that dx dt, sorry, dy dx. It's just equal to this divided by this. So you have 3t squared minus 4. And this is all divided by 2. Yeah, lots of space just for this one question. Again, don't get thrown off too much by it. Okay. And then in the second part, we're going to make use of the answer we just got from there. So we're looking for all the points x, y, at which the curve has a horizontal or vertical tangent. So we need to find both. Again, remember from just Calc 1 concepts or just ideas that whenever your curve has a horizontal tangent, it means your slope is 0. Right? And the only way that it's actually equal to 0 is the numerator is equal to 0 while the denominator is not equal to 0. Because if they're both simultaneously 0, you have 0 over 0, which is your indeterminate case, meaning it's not necessarily going to be a horizontal slope. So you need to make sure that, and again, I'll write it out in a sec, but just conceptually speaking, you know, your slope has to be flat, 0. And in the vertical case, obviously it has to be undefined, which means the denominator is 0 while the numerator is not 0. So I'll write that out. So first we have horizontal tangents. Horizontal tangents. This implies that, again, the numerator, meaning dy dt, is equal to 0. And if we take a look at what we have for dy dt, we have 3t squared minus 4. So this means that 3t squared minus 4 has to equal to 0. And here, it's just a matter of solving for t. So you have t squared is equal to 4 over 3. Here, it's really important to remember that you're taking the, you have the plus or minus, because again, if you square both sides, you have multiple solutions, 2 solutions. So in this case, t is equal to 2 over, or sorry, plus or minus. Yeah, I almost forgot that there. So plus or minus 2 over root 3 would be your answer here. You are definitely able to rationalize this. In this case, again, it's one of those kind of situations where you really don't necessarily have to. But yeah. So in this case here, sorry, I should also write that dx dt is not equal to 0. So the only kind of applicable part of this right over here is just checking to make sure that for that same point, or whenever you're plugging it back into your equations, just making sure that for these values of t, you don't have any overlap between dy dt or dx dt being 0. Okay, so in this step over here, there are a few different ways of doing it. You can either directly plug things in now, or you can find the vertical tangents points first. Doesn't really matter. The way I had done it previously was just plugging in the t values now, which I'll just do. So first you have t when t is equal to 2 over root 3. I personally had a small struggle with this question because I tried simplifying it way too much. And then later on, when I took a look at their solutions, they really didn't simplify too much. So I'll go with that in this case. So you plug this in. Again, what you really need to be careful here is where you're plugging things in. Over here, we're finding the solutions where dy dt and dx dt are equal to 0. But when we're plugging it back in, we need to make sure we're plugging it back into these parts over here. So for x of t, for x of t is equal to t squared minus 3. So we have our points x, y. Okay, so you plug this in, again, t squared. So we're trying to square this. So obviously you square the top, so you get 4 over 3. And then minus 3. So 4 over 3 minus 3. That's your x component. And then your y component, again, is determined by t cubed. Excuse me, minus 4t. So t cubed in this case is 8 over root 3 cubed. Then minus 4t. So minus 4 times this. So minus 4, so minus 8 over root 3. And that would be your first point. Again, I made the mistake of trying to simplify all of this. Definitely don't need to do that. You can just leave it like this, or at least they did leave it like this. So that's t is equal to positive 2 over root 3. Now we can consider negative 2 over root 3. So in this case, again, t squared minus 3. So the x component stays the same because, again, we're just squaring this. So it's still 4 over 3 minus 3. Here, again, we have t cubed minus 4t. So t cubed, again, because we're cubing it, this is now negative. So you have negative 8 over root 3 cubed. And then minus 4 times this, so plus 8 over root 3. That'd be your solution there. Okay, next we can move on to the the vertical tangents. So let's do that. So we have the vertical tangents. Or just vertical tangent. I'll tell you there's only one in this case. So this again happens when you have your denominator equal to 0. So in this case, dx dt. Here I should probably write and. Yeah, I'll write and over here. Yeah, so this should be simultaneous. They should be happening at the same time. So this and dy dt not equal to 0. So when this happens, we have, again, dx dt is over here. So 2t. So we have that 2t is equal to 0, which obviously means that t is equal to 0. Plugging this in, we have t is equal to 0. So our point x comma y, much simpler in this case. When you plug in t is equal to 0, here you just have 0 minus 3, so negative 3. And then for y, you have everything in terms of t, meaning you just have 0. 0. Okay, and then from here, you can write a conclusion statement, which I will also just do. So you can say, therefore, you have horizontal tangents at the points. I'm too lazy to rewrite them, so I'll just copy and paste them. But obviously on a test, assuming you have enough time, it's best practice to fully write things out. But because I have the liberty of an iPad, I will not. And this point here. And then, and a vertical tangent. That's negative 3, 0. The good thing about math is with these answer statements, you can be very grammatically incorrect to some degree by writing incomplete sentences, as long as you get the idea across. Okay, next we want to find the equation of the plane that passes through the point 3.14 as a pie joke, and contains the line x of t is equal to 4 minus t, y of t is equal to 2 minus t, and z of t is equal to negative 3t. So in this case, what we want to first do is kind of what I like to say, extracting the equation of the line. We can do this by identifying the points, which is just the constants, as well as the coefficients of the t term. So in this case, we will extract. So we have r of t. And again, we can write this simply just as the point plus the plus t times the direction vector. So in this case, in terms of the point, for x, we just have 4. For y, we have -1. And then for z, we have 0. Okay, so again, this is a direction vector. We can, and then plus here, yeah, I'll just write, or sorry, this is just a point, not a direction vector, apologies. So plus t. And then t, you can just imagine as just extracting, the coefficients. So -1, 2, and then -3. Okay. So remember, when we're finding the equation of a plane that passes through anywhere, really, in this case, it's obviously with a point and a line, you're going to need a normal vector. And once you get the normal vector, it becomes pretty easy. Getting the normal vector is usually the hurdle or the challenge of this question. But yeah, so in this case, we have one vector already. Again, remember to find the normal, you need 2 vectors on the plane. In this case, we have one right over here, but notice that we also do have a point and another point. So we can form another vector and then take their cross product. So in this case, I will set some variables. So let's say let's A, or set some vectors A. We'll call this vector over here. I think that's what I did. Yes, direction vector of the line. So in this case, -1 to -3. Make sure I got that right. Yep. And then we can also just let, we'll do this. So we'll let P be the point. So let's just say 4, -1. Oh no, P I let 3. Okay, you can do either way. You can let P or Q be either of the points you have. In this case, I'll just do it in the order that I had it written down in. So P, and then let's Q. Q will be the point that we got from the line. So 4, -1, 0. Okay. From here, we need to find, here we'll also write it here. So let B, well, let's do it in one step. And let B, do I have enough space? That's enough. And we'll let B equal to PQ. Maybe we don't have enough space here. We'll write it down over here. So let B equal to PQ, which again, we can solve by just subtracting the components of P from Q. Meaning you do 4 minus 3, -1 minus 1, 0 minus 4. And that will get you 1, -2, -4. So 1, -2, -4. Again, we get that by subtracting these. So 4 minus 3 gets you your 1, -1 minus 1 gets you your -2, and 0 minus 4 gets you your -4. And then from here, the usual way of denoting the normal vector is using a vector n. So we can just let n equal to the cross product of a and b. And yet again, we'll just use the Miss-Havrat method. So we have b, here, let me underline these. So we have a over here, b over here. Now we're just going to cross them. So in this case, we do the same method. So we have -1 to -3, -1 to -3. I just want to make sure, yes. Okay. And then we have 1, -2, -4, 1, -2, -4. Cross out the left and right kind of edges. And then from here, we can compute what n is equal to. So here, again, I'll just kind of do this sort of in my head. So you have 2 times -4, which is -8, minus -2 times -3, which is +6. So you have -8 minus 6, so you have -14. And that's what you get when you do this, multiply by this, minus that multiplied by that. Okay. And then next part here, you have -3 times 1, which is -3, minus -4. Again, there are lots of negatives here. So you have -3 times -1, which is -3, minus -4 times -1, which is just +4. So -3 minus 4. So you have -7. And then here you have 1 times -2, which is 2, minus 1 times 2, which is 2. So you have 0 in that case there. And that right there is your normal vector. And again, we can think of these components as A, B, and C, which will come into play when we determine the equation of our plane. So generally speaking, the equation of our plane is of this. So I'll just write the therefore. So the equation of a plane. Write it as such. So we have A, which is again the kind of x, so like the first component of the normal vector, times x minus x naught. And again, I'll explain what x naught, y naught, z naught are, but hopefully that's already pretty clear. Plus b times y minus y naught. And then plus c times z minus z naught. And this is equal to 0. So this is one of the ways of doing it, which I personally find to be the easier way of doing it. The other way of doing it is to just simply plug it in terms of like ax plus by plus cz plus d, and then you plug in a point to solve for d, whereas in this case, you can just plug everything in directly. I find it much more direct. So plugging in our values, we then get a, which is negative 14, times x. So x naught, y naught, z naught are simply just like part of the points. Like it's any point. So we have 3, 1, 4, and then we also have this other point, 4, negative 1, 0. It does not matter which one you use. You'll still get the same answer at the end of the day. So we'll use 3, 1, 4 just because the solutions use 3, 1, 4. So you have x minus 3 plus, or in this case, minus 7, so plus negative 7 times y minus 1, so 3, 1, 4, plus 0 times z, or z minus 4. Obviously, 0 times that is just equal to 0. So you are left with negative 14 times x minus 3 minus 7 times y minus 1 to 0. And this is your final answer. I'll just box it in. Okay, very nice. Okay. Yeah, continuing with question number 5. We now want to find the area of the region bounded by one loop of the polar curve r is equal to 1 minus cos of 4 theta. So with a question like this, usually you want to try to sketch the graph first. But in this case, it's really difficult to sketch that accurately to a point where you can actually use it. When you know that, regardless, when you see something like this, you already know that there's some symmetry involved. And you can always, in this case, you can almost just try to assume what it may look like. Quickly, I'll roughly draw what it does end up looking like. So something along these lines. But the point is, in this case, you can determine sort of like how or when one loop is formed in terms of the values of theta, simply by calculating when r is equal to 0. So you're solving for the zeros because regardless of how it's drawn, you know that a loop is formed when you start at 0. You do whatever it is, and then you eventually have to come back to 0 like this. And we can, again, just kind of do that and bypass the need to actually draw the graph by solving for these zeros algebraically. And yeah, for these ones, again, you can assume that there is symmetry involved because if you're finding the area bounded by one loop, obviously the other loops in this graph can't be different than one loop. So they're all the same, obviously. So in this case, it's safe to assume that you can just find the zeros, and then you can assume that you can integrate over that interval. So what this looks like here is, yeah, first we want to find the zeros. So find the zeros. Okay. And to find the zeros, again, we just simply set r equal to 0. So we set our function over here equal to 0. So yeah, so r is equal to 0. Meaning our function of r in terms of theta, 1 minus cos 4 theta. Or sorry, not 4 cos theta, sorry, cos of 4 theta. If I did say 4 cos theta previously, I hope I didn't. It is cos of 4 theta. And we know this is again equal to 0. And now we can solve. So we can add 1 to both sides, or sorry, not add 1, but add cos of 4 theta to both sides. You get the cos of 4 theta is equal to 1. Again, you don't need brackets here because it's unambiguous. Okay. From this step, again, you keep in mind that even though you have 4 theta here, you can solve for it as if it was just any standard like single variable. Like if you have like cos of x here, you obviously know that you're looking for wherever cos of x is equal to 0. So it doesn't matter this is 4 theta. It could be whatever you want, star. One of my teachers used the carets. But yeah, so in this case, you know that cos of something, when you take the cosine of some angle and it's equal to 1, you know that something has to equal to either 0 or 2 pi, right? So we know that when cos of something is equal to 1, we know that happens when cos is equal to 0. So if you imagine like 0 over here, or 2 pi. So if you imagine the graph of cosine, again, looks something like this. Happens here and happens here. It happens once a period. So in this case, you have that. So this then tells you that 4 theta is either equal to 0 or 4 theta is equal to 2 pi. And then from here, you can solve for theta. So here, theta is equal to 0. Or you divide both sides by 4, you get theta is equal to pi. You get 2 pi over 4, which is equal to pi over 2. So this right here tells us that when theta is between 0 and pi over 2, we know that one loop is formed. So we'll just quickly conclude that right here. So we can say, therefore, one loop is formed. That formed from, let's say, between 0, when theta is between 0 and pi over 2. Okay, from here now, we're simply looking to find the area bounded by this region. So we can, again, recall the formula. Again, I also always do recommend writing out the general formula, especially when you're doing practice, but during a test, it's obviously not necessary. So you have the area, again, this is for polar coordinates, is equal to the integral between alpha and beta. Again, alpha and beta are your limits of integration here. So the kind of bounds of theta of, again, 1/2 r squared d theta. You may see this written as f of theta. Obviously, r is a function of theta, but we'll leave it like this. So now we can plug in the known values. So we know that alpha and beta are 0 and pi over 2 respectively. So pi over 2. The 1/2, I guess you can move out front. So, it doesn't really matter if you keep it within the brackets or not. So 1/2 r squared. So we know that r is equal to this right over here. So I'll just write it fully out and then I'll slowly expand it. So we have 1 minus cos of 4 theta squared. Yeah, in this case, I'll drop the bracket. So 4 theta squared d theta. And then from here, it's a process of manipulation. And there's one small trick in between that you really should know. It's really commonly used, and it'll come up quite frequently. So first, though, we will just expand again. This is of the form a minus b squared. So we have, again, 1/2 times the integral of 0 to pi over 2. In this case, you can view this as a minus b squared. So a squared minus 2ab plus b squared. So you have 1 minus 2 times a, so 2 times 1 is 2, times b, cos of 4 theta, and then plus b squared. So cos squared of 4 theta, d theta. Okay, from here, we're going to use, again, a similar trick that I'm not sure if we used it previously or not, but it's the double angle formula. So I'll write it over here on the side. I'll write it in terms of x, but again, we keep in mind that even though we have 4 theta, we can treat that as an x. So I'll quickly derive it too. So I think, I do have it in mind. So you know that cos squared of this, let's say x for now. So x is equal to 1/2 times 1 plus cos of 2x. Quick way, or even just how it's derived, is simply you start with the double angle formula. You start with cos 2x. And in this case, if you're looking for cos squared x, you use the form where it's cos of 2x is equal to 2 cos squared x minus 1. And then from here, you solve for cos squared x. And you do this by adding 1 to both sides, then dividing by 2. So you have 1/2 times, again, 1 plus or cos 2x plus 1, doesn't matter. So that's how you would derive it, even if you didn't memorize it. And I'm pretty sure at the very end, you do have the double, or you don't have it directly, but obviously you can solve for it over here. But obviously it's better to not rely on the formula sheet. The formula sheet honestly isn't too useful. For the most part, if you're really nervous about like some trig values, you can obviously refer to it. Anyways, so from here, our goal is to convert these two, or no, sorry, this right here is fine. We can integrate that normally, but this right here we want to change. So we have cos squared theta. We can think of x, you can do a substitution if you really need, but you can think of x is equal to 4 theta. And if you plug it into this formula here, you get that cos squared of 4 theta is equal to 1/2 times 1 plus cos of 2x, so 8 theta in this case, meaning we can replace this, which is right over here, with this right over here. So 1/2 of 1 plus cos of 8 theta. So here we have, this is 1/2 times the integral 0 to pi over 2 of 1 minus 2 cos 4 theta plus, and again, yeah, exactly that. So I should have written down, but it's fine. So you have 1/2 times 1 plus cos of 8 theta, d theta. And then in the next few steps, I'm just going to simply expand it and collect things together just so it's easier to integrate. So again, you have 1/2. It gets a bit repetitive writing 1/2 and times the integral, but it is what it is. So in this case, I won't fully expand it. I'll explain what's happening. You distribute this 1/2 and you get 1/2 plus 1/2 cos of 8 theta. This 1/2, we can just combine it with the 1 we have up there just to get 3 over 2. So we have 3 over 2 minus 2 cos 4 theta plus 1/2 cos of 8 theta, d theta. And then from here, we're at a step where we're able to integrate each of these functions. So now we can just integrate. So we have 1/2 times integral of a constant. You just slap the variable in front. So you have 3 over 2 theta minus 2 cos. So in this case, you can ignore the 2 for now. Imagine what happens when you ask yourself the derivative of what is equal to cos of 4 theta. So obviously it's sine of 4 theta. But you do have to imagine what happens when you do take the derivative of this. You get this extra times 4 term. So we need to multiply by 1/4. So we have negative, so negative 2 over 4, so negative 1/2 sine of 4 theta. And then very similar idea over here, except you'll have to multiply by 1 over 8. So you have 1 over 8 times 2, so 1 over 16 sine of 8 theta. Again, this is being evaluated at 0 and pi over 2. And again, you can always do quick sanity checks by taking the derivative of this and checking if it's equal to this, which it will be. Take the derivative of this, it's just 3 over 2. Take the derivative of this, you have negative 1/2, times cos of 4 theta times 4. The 4 and the 2 will get you your, get you your negative 2. And here, same idea, you have 1 over 16 times cos of 8 theta times 8. 8 and 16 cancel out for 1/2, and you get exactly back here. Okay, and then from here, it just becomes using FDC, Fundamental Theorem of Calculus, Part 2, for evaluating definite integrals. But notice that whenever we do plug in pi over 2 or 0 in here, we will always get sine equal to 0, because here we have 4 times pi over 2, which is equal to 2 pi. Obviously, sine of 2 pi is equal to 0. Same idea over here, except it should be 4 pi, it's still equal to 0, and obviously sine of 0 is 0. So these two terms are effectively irrelevant. But yeah, for this, we can just directly plug in this pi over 2. So we have 1/2 times 3 over 2 times pi over 2. And then multiplying everything out, we get 3 pi over 8. And this right here is your final answer. In this case, yeah, you can definitely write a conclusion. You can say, therefore, yeah, we'll just do it. So you can say, therefore, the area bounded is 3 pi over 8. They didn't really specify units, so you can just say units. Unit squared, I guess. But yeah, so again, the big trick here was mainly implementing this right over here. So actually, here, I'll quickly write it. So when it is uploaded, you can say x is equal to 4 theta. Meaning here you get cos squared of 4 theta. It's equal to 1/2 times 1 plus cos of 8 theta. So this right here is kind of the core component of actually integrating. Everything else is simply leading up to the setup, which is all of this work right over here. Okay, next question. So we have, let's see, be the curve of intersection of the following surfaces. So I'll just tell you this is a sphere, and I think this is a cylinder of some sort. Regardless, in this case, it's easier if you do visualize it, but you don't really need to. The idea is you want to find some parametrization in terms of x and y, and then you write z in terms of that one parameter. In this case, we'll use t. So if we look over here, we have z, and our goal is to kind of get x and y on their own, so we're able to find some kind of substitution. But the most common one here, honestly, is just always using x is equal to cos and y is equal to sine, and we'll show you why you're able to do that. So if we treat this as equation 1 and this as equation 2, if we plug 2 into 1, we get the following. So you have x squared plus y squared. And then z squared, so we know z is equal to this, but obviously if you square it, you know, z squared is equal to x squared plus y squared. So you have another x squared plus y squared, and you know this is equal to 2. Obviously, these you can collect them together. You get 2x, here, I'll just write it out. So you get 2x squared plus 2y squared is equal to 2. So obviously x squared plus y squared is equal to 1. With this, you can then just take x and y to be cos and sine, respectively. So here, say let x equal to cos of t, and then let y equal to sine of t. And then from here, we still need to find some kind of parametrization for z using x and y. But good thing is we have that right over here. So plugging this in, we can say then, so you have z is equal to the square roots of cos squared of t plus sine squared of t. I'll draw a bigger square root sign. Oops. Third time's a charm. Okay. And then obviously, though, we know that the inside simplifies to 1. The square root of 1 is just 1. And then here you can say, therefore, your vector function, r of t, is equal to cos of t, sine t, and then just like that. All right, and then in part B, we want to use our answer from part A to find the direction vector of the tangent line to C, or curve, when t is equal to pi. So all this question is really asking us to do is simply find the derivative of r of t, so r prime of t, and then simply evaluate at t is equal to pi. So let's do that. So here, I'll just copy down what r of t is equal to. So r of t is equal to this, and then we know that r prime of t, we can again just take the derivative of each component. Derivative of cos is negative sine of t. Derivative of sine of t is cos of t. Derivative of 1, obviously it's 0. So we're left with this. And then from here, you're just evaluating r prime t at t is equal to pi. So we're plugging this in. So negative sine pi, cos pi, 0. Sine pi, obviously it's 0. So you have 0. Cos pi, negative 1. And then 0 is just 0. And this would be your final answer. So again, yeah, as usual, you can just write a conclusion statement if you'd like. You can say, therefore, the direction vector of the tangent, the direction vector of the tangent is this, so 0, negative 1, 0. And again, usually in high school, you get docked for not writing a conclusion statement, but honestly, I feel like I usually either do write it or they truly don't care. But yeah, there's that. Okay, last question here. We want to, again, first, it's a big question. Usually they'll have one big question at the end. We want to sketch the points r comma theta, which lie on the polar curve. R is equal to 1/2 for theta being between pi and 2 pi. So the first thing you want to keep in mind when doing this is obviously knowing what the graph looks like when either r or theta is fixed. You can always picture this. So if you imagine r being fixed and theta varying as like a free variable, theta just goes wherever, but obviously the radius is fixed, so that's simply just a circle. What you have to be careful of is, again, identifying where you're drawing the circle between in terms of the theta values. I just drew this on a gridded paper just so it looked normal, but obviously on a test situation, you can just very briefly sketch that. Say this is like negative 1/2, this is negative 1/2, this is 1/2, and then that would be sufficient, honestly, but yeah, that's the idea there. Okay, for part B, you want to sketch the polar curve r is equal to sine of 2 theta for 0, for theta between 0 and pi. In this case, this is more sketchable than like 1 minus cos of 4 theta. If you do need to use a table of values, definitely go for it. But you can quickly see that if we kind of recall stuff from advanced functions, I guess, you have the period is equal to 2 pi over k, where k is this value in front of our variable. So we know it's 2 pi over 2, which is equal to pi. So we know our sine function will repeat every pi units. So in this case, we know we just have one kind of iteration of our graph, which is definitely sketchable. So let's do that very briefly. Yeah, it's going to be a bit butchered, but oh well. So pi over 4. In this case, it makes sense to use pi over 4, pi over 2, 3 pi over 4, then pi, simply because we're just graphing between 0 and pi. So roughly over there, you have pi over 2, 3 pi over 4, and then pi. So again, recall that we do have theta on this axis and r on this axis. And then it's going between 1 and -1. Again, it's just like any other sine graph, except you're just kind of squishing it a bit. But based on our scale, it's going to look the same. So something like this. Let's see. Nice, second try. Okay, something like this. And again, you only need the general shape. The great thing about sketching polar curves is as long as you have the general idea right, they're never really going to get that specific with it. But yeah, so now we have this. We're not quite done yet. We still do need to sketch it in terms of polar coordinates. We kind of just treated these as our typical Cartesian or kind of rectangular coordinates. So let's do that over here. Yeah, and GoodNotes doesn't have a feature for dotted lines yet, unfortunately. So you'll just have to deal with a red line to indicate where the angle is going. But oh well. Okay. So in this case, you obviously start where theta is equal to 0, which is the kind of right side of this axis here. And then from there, you notice that at pi over 4, you're going to hit like a kind of like the furthest point at 1. So we can roughly draw that over here. Actually, no, here, we'll draw it with the red line. Is that how I sketch it? Yeah, that is. Okay. So this line here will represent pi over 4. And then we'll also need to make use of the corresponding 45-degree lines over here in a second. We'll deal with that for now. So here, again, we start at 0, and then eventually, once our angle hits pi over 4, we want to be at roughly 1. Again, it's a rough estimate, but we'll be at 1. Let's just assume it's over there. And then right after that, we're coming right back. So once we hit pi over 2, we're coming right back to the origin. So what this part roughly looks like is something like this. Let's see if we can draw that better. Something like that. That's good enough. Actually, no, I can do a better job. Let's see. I'll draw that further out. Let's see if that helps. Oh, I got it so nicely the first time. Let's see. Okay, that's good enough. That's good enough. Okay. And then, so that's this portion right over here. This next portion over here, you need to keep in mind the convention for polar coordinates, and that when r is negative, it's reflected over the pole or across the pole effectively. So typically, if our r values were still positive, we would definitely be going over here and then back down over here. But because they're negative, they're again reflected over the pole. So instead of going from here to here, you are effectively going from here to here and then here to here. But I'll draw that a little better. So roughly over here is where a point goes. That's actually not bad. Okay, we'll go with that. Obviously, if you're drawing with a pencil, it'll be a bit smoother. GoodNotes doesn't have very good shape recognition or drawing it, unfortunately, but it'll look something along these lines right over here, pretty much. And here, I'll label these as well here as 3 pi over 4. The bottom part, you don't need a label, but it's simply just there for reference because you are reflecting it over the pole. But that would be for this part. Okay. This last part over here is where it gets a little tricky. It's also where I personally lost marks on the midterm, but let's get that in here. Okay, so if we kind of just, yeah, I'm going to copy and paste these graphs together. I'll show you what it roughly looks like, and then I'll also show you, yeah, I'll enlarge it a bit. Yeah, that's better. Will I need the extra space? Yeah, I probably will. Okay, so then yeah, I'll copy this over. Oops, that's deleting it. Okay, yeah, this is definitely a little butchered. Okay, it's a good thing I have a Desmos image ready, but it looks something along these lines over here, where, yeah, again, I unfortunately don't have the enlargement correct, but you're looking for the area under uh, both polar curves. And it's important that you did do the previous two parts correctly, because you're actually just looking for the area enclosed over here by this area over here. Or sorry, no, right over here. Or yeah, right over here, actually. Let me make sure that's right. Yeah, I believe it is. Sorry. So this area right over here. Right over here. And it gets confusing because I think initially I even thought you were just subtracting the two functions, but after you do get the zoomed in picture, you'll see why it's slightly different. So yeah, I have it right over here. Okay. So the intuition or the idea behind why it's probably not what you initially thought it was is this. We'll draw it like this over here with this kind of red and orange color going. Okay. So again, remember with polar, like area and polar coordinates, whenever we're trying to find area, you always want to imagine like a kind of arm sweeping through and covering the shape. And if you actually do imagine that, you'll notice that this portion right over here, actually, I'll color it in this kind of yellowish orange. So this portion over here, if you actually notice, it's effectively the green curve, which again is the loop of our sine of 2 theta, right? So I'll kind of label this here, the orange, as the area produced by r is equal to sine of 2 theta. And then the area over here, which I labeled in red, this right over here, which again, I'll do a lousier job of coloring, but you will get the idea. This entire area over here is actually covered by the inner curve, which is r is equal to 1/2, that circle. The thing about this question you have to realize is, again, the big role that symmetry plays in this. So not only are we able to, again, the reason why we have this kind of top portion and not this bottom portion, again, is symmetry. So we can equivalently calculate the area as if the circle was over here. And then again, because of symmetry, we also only need to do the work for calculating the area of these two regions over here and then simply doubling them. So let's do that quickly over here. I guess I'll do it in the respective colors. I think that makes most sense. Okay, so in this case, you also would need to find the intersection point over here. I believe it was pi over 12, but we can verify that quickly over here. So the way you do that, again, is just finding the intersection between these two curves. So you just basically set them equal to each other. So you have sine of 2 theta is equal to 1/2. And then again, same idea, you're finding where sine of something is equal to 1/2, which again is at pi over 3, I believe. Here. Oh, maybe it is useful, just so I'm sure. Sorry, pi over 6, yeah, this happened at the earlier stages. I don't know why I'm bugging it. It happens earlier, pi over 2, sorry, or 1/2. So in this case, you know that 2 theta is either equal to pi over 6 or 2 pi is, or sorry, not 2 pi, 2 theta is equal to, again, in the second quadrant where sine is also positive, 5 pi over 6, meaning that theta is either equal to pi over 12 or theta is equal to 5 pi over 12. Obviously, because we're dealing with the first quadrant here, we'll be taking the first option of pi over 12. So we know that for this part over here, we're integrating between 0 and pi over 12. For this portion over here, we're integrating between pi over 12 and, I should write this over here. Hopefully it's clear. This is pi over 4. And then we can just multiply that by 2. So let's do that over here. So again, in orange, I'll just indicate just this portion over here. In red, I'll indicate just this portion over here. And then we'll double the entire answer. So over here, we have the area. This time I won't write out the alpha beta, like the general form. Hopefully you do understand that by now. So again, this is between 0 and pi over 12 of 1/2 times r squared. So sine squared of 2 theta d theta. So again, this is the area of the orange portion. And for the red, similar idea. So the area is equal to the integral between pi over 12 and pi over 4 of, again, 1/2 times r squared. So 1 over 4 d theta. This you can obviously simplify. We'll simplify once we combine them together, but this you can just have as 1 over 8. So then the total area is simply equal to the following. So it's equal to 2 times, I'll write it in big brackets. So just the, yeah, that's better. So again, integral between 0 and pi over 2, sorry, pi over 12, times 1/2 sine squared of 2 theta, d theta, plus the integral. Let's get that better. Yeah. Integral between pi over 12 and pi over 4 of, again, 1/2 times 1 over 4, so 1 over 8 d theta. And I believe that should be the final answer. So honestly, the bigger part of this question comes down to actually understanding what's going on. And I definitely did simplify it a little bit. So definitely, like if you do have the textbook, there are similar questions to this that I would recommend checking out. But this would be considered one of the harder questions. So something like this definitely wouldn't come up on the final exam. Something like number 5, yeah, something like number 5 here would be much more appropriate as like an exam question. But for term test, this is definitely fair game. It's simply like a more complicated scenario where you do have to think a little more rather than just simply subtract the two functions like I initially did when I did the midterm as well. Yeah, I definitely didn't mention that at the beginning, but you're not allowed a calculator either, which is where things may get a little difficult, but that's why you got to practice without a calculator to begin with. But yeah, you definitely, again, won't have access to something as accurate as this, but as long as you are able to get the general idea over here, it actually might even be easier to see over here, right? You can kind of see how, let's say between, what's a good example? Yeah, if you imagine integrating here, like if we draw this over here, you can imagine that integrating between like this portion over here, for example, or like a smaller portion over here, would be like this over here. It's kind of magnified. So in this case, you definitely want a better sketch, obviously, but you can only do so much. But do be aware that this is a possibility in terms of what can be tested. Okay, that's pretty much it. If there are any typos or any errors, do let me know. I actually didn't. Here, I'll check it over right now. I definitely should have checked before, but oh no, I did get it right. Nice. Okay. So yeah, again, however, yeah, these are the official solutions from provided by the instructors. I'm really not sure if I'm allowed to share them, but I'll definitely share mine, which is pretty much identical because I based some of it off of theirs. But mostly it's pretty much what I did on my own midterm as well. But yeah, perfect. Thank you for watching.